So, welcome to the next talk, to our session. The next talk by Abhishar Dar. Title by light cone spreading of perturbation and the butterfly effect in classical spin chain. Very impressive title. Please start.
Thanks. So I would like to thank the organizers for asking me to talk here, and I apologize for not being able to attend the other talks. So it turns out that I didn't realize that there's another school that I'm organizing which is running at the same time. So obviously I can't be at both places. So anyway, I'll try to explain something about some work on dynamical systems that we have recently been doing at ICTS. So this is about light cone spreading of perturbations in the Heisenberg spin chain, and this work is done with student Abhijit Das and a former postdoc Shorish Chakraborty, and then lots of colleagues at ICTS, Shubhro Bhattacharjee, Anupam Kundu, and Samriddhi, who's also here, and Roderick Mosner at Dresden, and David Hughes at Princeton. Okay, so this work just got accepted in PRL, and this is a kind of old version that is there in the archive. Okay, so the outline of my talk is. Okay, so I started. Okay, so I'll talk about. This is correct, is it? This watch? It's correct. So I'll start. Okay, 40, yeah. Okay, so I'll talk about in general, it's a basic idea of chaos in classical systems, and then so usually one talks of like growth of perturbations, but one point is also like if there's a localized perturbation, how does it spread? Okay, so that's the new aspect that I'll talk about today. So there's something called out-of-time ordered correlator that has been used in recently in quantum systems to probe chaos in quantum systems, in non-integrable quantum systems, and this has been used also as a to understand propagation of information in quantum systems. And what I'll talk about is like a classical version of this object, this out-of-time ordered correlator. Okay, so I'll briefly mention what the basic idea of this out-of-time ordered correlator is, and then I'll basically present numerical results that we have obtained for this Heisenberg spin chain, looking at this particular aspect. Okay, so basically this is chaos. Basically butterfly flying in Beijing can cause a tornado in some far-off place. And so, of course, one can, one question that we're going to ask is like, how long does it take for the tornado to occur? Okay, so eventually it's going to be chaotic, but how does it propagate? Okay, so again, sort of more precise definition of chaos is, let's say I have a dynamical system with n variables, and they follow a set of first-order nonlinear equations. And so then I start from two different initial conditions, ZA and ZB. And then I evolve both of them with the same set of equations, and then I ask like, how does this difference grow with time? Right. So, so after time t, this is the difference, and the definition of chaos is that if at large times I find that the distance divided by the initial distance in the limit that this initial distance goes to 0, if this diverges exponentially at large times, then the system is chaotic. Okay? And then this lambda is called the Lyapunov exponent of the system. So this lambda could, of course, depend on where initial point I start in phase space. And okay, so this is the definition of chaos. Okay, so now we want to look at propagation of chaos, which means I have these dynamical systems which has some notion of space. So X is, let's say, the positions on some, there's some lattice, and I put a perturbation at some localized site, and then I want to ask, like, at a different site, if I make an observation, then how does this ratio again grow with time? Okay, so earlier what I was doing is I was looking at the full distance of these 2 points in the full phase space, but now I'm just asking, like, at a given point, I look at some local observable, And I want to ask, how does this ratio grow with time? Okay, so then of course we still expect that, I mean, at large times it should, I should still get the same, because each matrix element should roughly behave in the same way. So eventually I should get that at any point, if I look at how the initial perturbation is growing, it should still grow with the same Lyapunov exponent. Okay. But there will be some space dependence and time dependence, and this is like, it will obviously take some time for the information to travel to some point, and we want to study how this propagation happens. Okay. So how long does it take before the perturbation is felt at some point takes, and how does this spatio-temporal evolution of this perturbation takes place? Okay, so I just want to give a simple example of like the kind of system we are looking at. So one can think of, let's say, a set of coupled pendula, where each degree is basically consists of a position of and momentum of the pendulum at the xth lattice point. So if we put a small disturbance here, then we can ask how it spreads. So let's say the initial disturbance is a small displacement of the position at the origin, and elsewhere it's completely undisturbed. Okay, so initially, of course, it's in some state QP, and then I just perturb the position of the particle at the origin. Okay, so now I am interested in this ratio. So now for a Hamiltonian system, I just want to point out that this ratio is actually exactly equal to a Poisson bracket. Okay, so this is the definition of the Poisson bracket. And if you use this definition, you can see that this ratio I'm looking at is basically the Poisson bracket of QXT and P00. Okay, so so this sort of question, of course, we ask in standard linear response. Like I have some dynamical system, and it's in, let's say, in some state, and then I make a small perturbation at some point, and then how does this perturbation spread? Right? So that's the usual question in linear response, and then we can, so here this average means like the system might be in equilibrium, and we do an average over initial conditions and then look at the typical response to the perturbation. So this response, of course, we know from linear response here that this is related to some correlation function, so some like equilibrium correlation function, so this is some spatiotemporal correlation function. Okay, so this is linear response. So now the object we are looking at in understanding chaotic behavior is actually kind of the square of this object and then take an average. Okay, and what we'll see is that this object behaves completely different from this object, and this has so it has different way. We want to understand how this signal spreads and how does it grow in time. Okay, so so now I want to just explain why, like recently, there's been a lot of interest in understanding this kind of an object or an analog of it in quantum systems. Okay, so in quantum systems, of course, the phase space details are replaced by a wave function, and then we know that the equations are linear, so there's no chaos in general. So usual characterization of quantum chaos is looking at various things. So one of them is like looking at level spacing statistics. So if you take a non-integrable system, for example, a system that you know is classically chaotic, and then quantize it and look at its spectrum, then you find that the level spacing distribution follows Wigner distribution instead of Poisson distribution. So that's a characterization of chaos. But you don't see usually you don't see if you look at the wave function, you won't, if you start from different initial conditions, they don't diverge exponentially. Okay, so now in a recent paper, so this set of people who work in string theory, they basically propose that what one can do is, so here I was looking at this Poisson bracket, but in a quantum system, supposing I look at the commutators and the square of the commutator, and the expectation of in some density, in some thermal state or in a pure state. So then this particular object, maybe it captures some aspects of chaos. Okay. So at least I expect that in the classical limit, this should behave exactly like like this object. So it's important that I square this object, because otherwise I'll just get what I get in linear response, and you don't see chaos in linear order. So you have to square this, and you replace the Poisson bracket by basically a commutator, and then look at its expectation. Okay. So this is a function of space and time, and then is it possible to see this Lyapunov growth in this system? Okay. So now one can see that actually, if unlike the classical system, this particular object in a quantum system at sufficiently long times, it will always converge to a finite value. Okay. So because if, let's say, we are talking of systems with a finite Hilbert space, so there you can show this will always go to a finite value. But now the idea is that there's still a, so initially it starts, let's say, from a very small value. So there is some time scale where you will see there's a growing scale, growing phase. And in that, there is some attempt to extract a Lyapunov exponent in that growing phase. And then there are some very interesting results, like there's a bound you can set on the Lyapunov exponent. Then there are things called Ehrenfest time and scrambling time. So scrambling time is like how long does this perturbation take to reach some point. And Ehrenfest time is, of course, the time at which a system becomes kind of classical. Okay, so in this context, various things have been discussed, like ballistic spreading. So it's found that this signal actually spreads ballistically. And the velocity with which it spreads is called the butterfly velocity. And it's related to some other stuff called Lieb-Robinson velocity and so on. Okay, so now what we wanted to do is basically, so in quantum systems, I mean, for some class of models, like large N gauge theories and so on, and some very special models, one can actually compute these objects and understand various aspects. But if you look at like a spin chain or something, then it's very hard to do numerics and get any detailed understanding of this particular object. Okay, so I mean this particular object. Okay, so we want to understand like what are its features of this particular how does it spread and how does it grow? Okay, so in quantum spin chains, it's very difficult to numerically compute this. What we wanted to do is, in a classical model, try to look at the same object and see what are its properties. Okay. So basically, we looked at this Heisenberg spin chain for various reasons, which I'll try to explain. So this is basically a one-dimensional chain of, let's say, n lattice sites, and at each side there's a spin, three-component spin sitting. With unit magnitude, and the interaction between the spins is just ferromagnetic, so they like to align with each other. And the equations of motion in this case is something called spin precision dynamics. So each spin basically sees an effective field due to the neighbors, effective magnetic field, and then it just precesses around that effective magnetic field. Okay. So the effective magnetic field in this case is just the sum of the nearest neighbor spins, L-1 and L. And then it's a spin precision around that effective field. Okay, so this is the dynamics, and this dynamics actually, even though it looks like it's not a kind of system with Q and position and momentum, you can doing some transformations, you can show that this has exactly a Hamiltonian structure. Okay, so it's completely Hamiltonian dynamics. Okay, so. Okay, so these are the equations of motion. So now the first thing that you want to understand is like what is what is linear response in this system. So how do perturbations at linear perturbations grow? And for that you could compute something like a spin-spin correlation. Okay, so basically it's like I put a small magnetic field at some site and then see how it spreads. So if I compute this spin-spin correlation, so this you can, so here I show data where basically you start with, so this average is over equilibrium spin configurations. So in this case, the data is for infinite temperature, which means I start with a random configuration of spins and then just compute this average over all initial conditions. Okay. So the correlation between the spin at site 0 and site x at time t. Okay, so so this is what I plot here at different times. So initially, it's a delta function, and then it spreads basically as a Gaussian. Okay, so initially I put a perturbation, and it's spreading like a Gaussian, and one can check that this is complete the scale. If I scale position by t to the power half, then all these curves collapse. So this is diffusive scaling, okay? And here we plot like C0t as a function of time. This decays as 1 by square root t, okay? So basically it shows that spreading of pulses is diffusive in this system. Okay, so similarly, so this is spin correlations, and you can also, so this model has like energy and spin are conserved. So all conserved quantities you can show have like diffusive correlations. So here it's like what I'm looking at is I just so I have this spin configuration, and let's say I suddenly apply a magnetic field at the origin. Okay, so then that spin is perturbed, and then I can ask how does the magnetization spreads, right? So let's say this at the origin I magnetize this spin, so then I can ask how does this spread. So I just look at the magnetization profile as a function of time. So this correlation function is basically effectively looking at that. This is completely equilibrium, right? Yeah. So, and this is infinite temperature, right? Yeah. So, okay. So perturbation spread diffusively as far as linear response is concerned. So this is for spin, but for energy also you can dump in some energy and ask how it spreads. That also spreads diffusively. Okay. So now we want to do the following slightly. Okay, it's a similar experiment, but we measured something slightly different. So basically, like I said, we take two spin configurations, which are identical at all sites except at the origin. So at the origin, I just move the spin to some different position. Okay, and both these configurations I evolve with the same dynamics, right? And then I look at the difference of the two spins at any point at time t. Okay, so then this is the object I look at. So dxt is delta sx, so difference in these two spins at time t, square of that, and then I average over all possible initial configurations. Okay, so earlier what I was looking at is just without squaring, I was looking at the average, so that's the linear response. But now I'm squaring it and looking at the average response. Okay, so this, of course, if you, delta Sx is basically Sa minus Sb. So if I square it, because S square is 1, so I'll get 1 minus Sa, Sxa, Sxb. Okay, so this Sxa is the spin at site X for the configuration A, and this is for the configuration B, both of which are parallelly evolving with slightly different initial conditions. Okay. Okay, so now if you look at this object, I mean, at large times, so initially, of course, if I'm looking at some far off site, the spins are exactly same. So this is just 1, right? So this is 0. So everywhere is 0 except at the origin, and then it's spreading. Okay, and at large times, what I expect is that these two spins should become completely uncorrelated. So this object should go to 0 and D should go to 1. Okay, so if I stay at some fixed point X and wait for long enough, then this object should go to 0. Should go to 1 at long times. So it starts from 0 and goes to 1 at long times. Okay, and okay, so but what we're interested, if we divide by delta S0 square, then of course it can diverge, and that's how this Lyapunov exponent is defined, right? So I hope this is clear, the definition of the. So I just want to point out that this object is basically defining the Lyapunov exponent, but now I'm doing it locally. Okay, so okay, so this is like a snapshot of if I take the difference of these two spin configurations at various times, time is going up. This is what it looks like. So initially only one spin is different, then the perturbation is spreading, so more and more spins are different. And you can see that if you, okay, this is like the perturbation is spreading kind of ballistically. Okay, so from this, so this is just a single realization. And then we want to do an average over lots of realizations and ask how does this signal grow in space-time. Okay, so this is after, so this is basically this object d of xt for a system of size 2000 spins. And I plot, so this is a contour, I mean kind of, so what this color show is, so in this blue color corresponds to the d being 0, which means the perturbation has not reached here. And this corresponds to d equal to 1. So the perturbation has already reached. Okay, so within what you see is that in this space-time plot, within some light cone, so we call it light cone just for reasons of like that seems to be the nomenclature. So, but within this, the perturbation has reached, and outside it's completely 0. Right? Okay, so and so then there's the associated velocity, and that's called the light cone velocity. In this case, it's some number 1.67. Okay. Okay, so okay, so now we want to ask, like, how does this? I mean, if you go outside the light cone, how does there's a front. So if I plot d of xt, so then inside it's 1, and then it decays to 0 outside some region. So we want to understand greater than. No, this of course depends on like for example, in this case, it would depend on the coupling constant. So I can, yeah, it just depends on the parameters of the model. Okay, so now, so if you look at the inset, what it shows is that this d of xt at different times. Okay, so like I said, at a short time, it's 0 everywhere, and in some small region, it's non-zero. And it saturates to a value 1. So, and then this front is kind of spreading. Okay. Okay. So now, so what we expect is that basically d of xt. So this is. So let me just write this here. So this is dl delta xt square of this and average. Right? And there was a factor of 2, which is not so important. And then if I, so what I expect is that this should kind of go as epsilon square e to the power lambda t. Okay, and of course this depends on where I look at. So, so what we expect is that it should have some form like this. Okay, so now let's look at this function log of d divided by epsilon square. So, and if I divide by time, then we expect basically this, if I look at this object, it should tell me what is this scaling function. Okay, so this I expect just from the fact that there should be exponential growth. So that's what we do here. So inside I just plot the bare data, and then I do the x-axis I scale by time, and then I take this log of d by epsilon square and divide by time. And then we see that there's a region where it, okay, so you get some collapsed data. Okay, so, okay, so, okay, so what you expect is that if you are, let's say, if you are, so there's a light cone x equal to v t. And if you are outside the light cone, then the signal should decay exponentially, right? It should decay very fast. So which means that this function should become negative. And within the light cone, so for so this we expect that lambda should be less than 0, and for x less than vct, we expect that lambda should be greater than 0. Okay, so so this is what you see that I mean, so there's some, so around, this is around 1.67 or whatever. So beyond that, it's less than 0, and out here it seems to okay, it's going to some value. Okay, so now this is of course with a finite epsilon, so I need to take the epsilon going to 0 to really get the positive part. Okay, so Okay, so I mean, you can do this dynamics in two ways. One is you can, of course, put a small perturbation epsilon and then see how this difference grows. Or you can already take the epsilon going to zero limit, which means you worked with linearized dynamics, and then compute this object d by epsilon square, where you have already taken the epsilon going to zero limit. So, of course, if epsilon is finite, then d goes to a constant, but d by epsilon square in the limit epsilon going to 0 goes to a, blows up. Okay. Okay, so now I look at this, again, the same signal, but as a function of time. Okay, and so as a function of time, what we, if I am sitting at a fixed x, then what I expect is that, so let's say if I plot dxt as a function of time at a fixed value of x, right? So for a long time, of course, it's 0, or it's extremely small. And then at some time, which is like time equals to x by vc, it should start growing, right? And it should start growing. And then, of course, I said that at long times, it will saturate to a value of 1, right? So, but if I look at the object d by epsilon square and then take limit epsilon going to 0, then you can see the exponential growth for all times. Okay, then there's no saturation. And in that case, you would see this basically, finally, there's the exponential growth. Okay, so if you work with the linearized dynamics, then you can actually get this thing. If you work with a finite perturbation, you'll always get a saturation. Okay, so here what I show is that I again take this log of this object and divide by time, and then plot as a function of time. And then here you have plots with the linearized dynamics and with the nonlinear dynamics. Okay, so this is at, let's say, at x equal to 0, and this is at x equal to I think 16, and this is at x equal to 32, x equal to 64, and so on. Okay, so at each point the signal arrives at a different time, and then it okay, so and then it saturates to some value, which is basically the Lyapunov exponent, right? So you can this one is the linear one, and the dashed line is the, so for some time, of course, they will follow the same curve, and then at some time the nonlinear curve will like it will go to 0, but the linear curve, it goes to the expected Lyapunov exponent. Okay, so one thing we immediately see is that wherever you start from, eventually you go to the same Lyapunov exponent at long times. Okay, and then in the inset, what we do is basically we try to extract this function lambda of x by t. So we scale by t by x this data, and then for the linear dynamics, you see that you get a perfect collapse. Okay, and then this function actually fits to some form like this. Okay, so this lambda of xt is basically given by some lambda L 1 minus t square. Okay, so okay, maybe I'll put xc here. Okay, so for x greater than outside the light cone, this is negative. And so the signal decays exponentially, and if x is inside the light cone, then it grows exponentially. Okay, and here basically the idea is like you have kind of a velocity-dependent Lyapunov exponent. So in this so you have xt plane. And depending on like which direction you look at, you get a different growth of the signal. Okay. Okay, so now, so one question you can ask is to try to determine this. So basically, we saw that there's a front like that, And if we want to find the velocity of this front in a precise way, we can ask like at what time does, let's say we are sitting at some fixed x, at what time does the signal grow to some threshold value, right? So it started from 0, and then of course, because this is a non-relativistic thing, the signal in principle propagates immediately, but it's extremely small. So to define a speed of reaching, we have to define a threshold, and we can ask when does the signal reach this threshold at a given x. Okay, so here what we plot is like at different x, we ask where, at what time has the signal reached, okay, a given threshold. Okay, so you get a straight line which corresponds to the fact that it's ballistic, but if you start from different initial condition, then you get some spread. Okay, so the time of arrival of the signal at a given point has a spread depending on initial conditions. Okay, so we were starting with from this random initial conditions. So there's a spread, and you can ask how this spread grows depends on x. Okay, so what we find is that the spread actually grows as x to the power 1/3. And then you can ask the distribution. So the distribution kind of looks like a Gaussian. So here you can fit the. So if you do this scaling, then basically it's very close to a Gaussian. Okay, so this is one interesting observation that there's a x to the power 1/3 broadening of the signal. Okay, so now from this observation, we actually find that there's a very nice possible connection to the problem of KPZ surface growth. So KPZ is Kardar-Parisi-Zhang, and it's a model of interface growth. So you have like a one-dimensional height surface, and then it grows following some equations. And this is a very well-studied model in non-equilibrium physics. And so what we find is that you can kind of construct a mapping of this model to some aspects of the Kardar-Parisi-Zhang. Okay, so basically what is the idea? So the idea is that, so here basically what we have is, okay, so we are looking at this signal d of xt, and initially it started as a small perturbation, and then it's, if we look at a given realization, it's basically doing some, it's spreading like that. Okay, so maybe I shouldn't plot this. So supposing I look at this object, okay, so we said that d goes like this. So if we take log of d, so that's basically lambda times t, and lambda we said is this, right? So this becomes lambda Lt minus some constant into x square by t. Okay, so if, a log of t basically has this kind of time and space dependence. Okay, so this is of course on average, but realization by realization there's some fluctuations, and so we can from the data that we got, what we saw is that these fluctuations have a t to the power 1/3 scaling. Okay, so there's some fluctuations. And which has a t to the power 1/3 scaling. Okay, so now supposing this object log of d, we call it h of xt. Okay, so now from the kind of observations we are doing, h of xt basically started like this, and then it's something which is on an average growing linearly with time, and then there's some quadratic profile, right, at a given time. So roughly it looks like, I mean, it looks like some surface that's growing. Okay, so therefore you might be tempted to think that maybe this surface is also given by the KPZ. So usually like any 1D surface has, is in the universality class of KPZ. So, so we might try to make an identification of this to the, like at least some properties should be similar. Okay, so therefore we studied, basically, we looked at this function carefully. And so one of the things that's known about this is that this eta distribution is, for the KPZ equation, is supposed to be a Tracy-Widom distribution. Okay, so this is one very interesting result. So whatever microscopic model you start with, as long as they're in this KPZ universality class, these fluctuations follow the K distribution. Okay, so therefore we looked at this distribution of H the fluctuations in this height profile from our numerical simulations. Okay. So, there are two aspects. There's this t to the power 1/3 scaling, and then this distribution should be Tracy-Widom. Okay, so this is what we got. So this is the distribution of this. This function that we obtained from this data, and you can look for the distribution by sampling different initial conditions. So what we find is that, okay, so this is the Bayer data. So because on an average the height is moving, and then that's the linear thing, and then there's some spread. And what we find is that you get this, if you do this scaling, then you have this collapse. Now, of course, the question is this Tracy-Widom, which so far, I mean, we find that you can't really fit it to a Tracy-Widom. Okay, so in that way, the connection doesn't work so well. But at least the t to the power 1/3 scaling is, and so we have some arguments why this, even though some aspects may be captured by KPZ, this particular scaling may not work for some reasons. Okay, so, right. No, there's no magnetic field. Right, yeah, there's no magnetic field. If you put a magnetic field, no, I think you'll still have, like, you should see the same kind of things. Like, there, of course, I mean, then spin is not conserved maybe, but energy is still conserved, so energy will diffuse. But if you look at this signal, you might see many of the features will be unchanged. Of course, it's interesting. Yeah, the universality class, I don't know, yeah, maybe it's not KPZ any longer. That's an interesting question, like how stable is this? Okay, so I think I have, basically I want to conclude. And so basically we have, in this study, what we have been trying to do is, basically this out-of-time order correlator has been did very extensively recently in quantum systems, and people want to understand how it behaves in basically the spatio-temporal characteristics of this object. And we have tried to look at it in this classical Heisenberg spin chain. And what we find is that, okay, so even though it's a system which is, if you just look at linear response, you find diffusive spreading of perturbations. But when you look at this object, you find that it spreads ballistically. Okay, so that's one sort of surprising result. Then, of course, you see this exponential growth, and then you have a moving front, which you find that it has the way this front broadens and so on is similar to the KPZ equation. This thing in this kind of systems, it's kind of useful to define this notion of a velocity-dependent Lyapunov exponent, which tells you that depending on the direction you look in space-time, you get a different Lyapunov exponent. Okay, so this idea was actually, I mean, we didn't know when we started this study, but we found that there are some old studies on, I think, coupled map lattices, where this idea of a velocity-dependent Lyapunov exponent was introduced. Okay, I'm not sure if this is the first study. Most probably, this is the first paper. Okay, and then there are also questions on. So this Heisenberg spin chain is a chaotic system. It's a non-integrable system. So you can ask, like, if you take an integrable system. So that's one of the main goals, to differentiate integrable versus non-integrable systems. How is it different if you take an integrable system? Okay, so at least there are many indications in many systems which suggest that, okay, so if you're an integrable system, then I mean, if you are within the light cone, you don't get an exponential growth. Okay, so this function for x less than vt within the light cone, this lambda is strictly 0 for an integrable system. So that's one difference. And then you can ask, outside the light cone, how does it decay? And there, you have some scaling properties. And there you find that for v, so this maybe should be velocity. Yeah, so outside the light cone, basically it has a different power. Okay, so a lot of integrable models show this kind of scaling form of this Lyapunov exponent. Okay, so so one other sort of very interesting question is, okay, so this I mean chaos of course is is something that you can is not very easy to measure experimentally, right? So, and it's not clear what this particular object we are that we are discussing, how to really measure it in an experiment. Okay, so there are like some suggestions which indicate that if you define information in some way, then information propagation is given by this object, and then in the quantum case, there's something called a Locksmith echo signal, which is also experimentally accessible. Which again kind of measures this particular this commutator square expectation. Okay, so I'll stop here. Thanks.
Is it similar to damage spreading? Damage spreading?
Yeah, that's I think okay. So yeah, it's in some sense it's the same question. But usually damage spreading has been seen in mostly kind of stochastic systems, right, with stochastic dynamics, maybe cellular automata. And yeah, in some sense the question is the same. Right, yeah, in some sense it's the same.
Applying a field, but by just changing the
configuration, right? Here we are doing exactly the same. It's basically changing the initial, so it's like damage spreading actually. It's very similar to damage spreading.
And Grasberger says that all
right, yeah.
DP universality class, damage spreading transitions are in directed percolation universality class.
So I don't know if that analysis will be done here. Yeah, that's an interesting question. But yeah, I mean, yeah, I'm not sure if that analysis, which is probably more for kind of cellular automata kind of models, maybe, or stochastic models, like sorry. Coupled map lattices, right? Coupled map lattices, but you are saying even the DP class, okay. So maybe that's an interesting question. Like, does it also belong to that class? Yeah, that's okay.
It won't be KPZ and DP at the same time.
At the same time. Yeah, that's asking maybe for too much. Right, yeah. Yeah, so we have some ideas of why it's not KPZ and how you can make it KPZ, which we are now exploring. Right, yeah. But DP, in DP also, do you see the spreading of the front? And it's
spreading exponents, etc. That might okay. Then you can at least compare with the DP things.
Right. Okay.
More question?
Probably I missed the point, this quantity D that you defined.
Yeah.
And so Lyapunov exponent generally is defined in the long time limit.
Yeah.
Time tending to infinity.
Right, yeah.
But here this quantity becomes one.
No, so that's what I was saying. If you take a finite epsilon, then of course D itself goes to a finite value, but when the Lyapunov really corresponds to D by epsilon square, and then epsilon going to zero limit, so then it can diverge to infinite, right? So it's the ratio which can go to infinite.
You've done this kind of analysis for the system that you had a picture at the beginning. I mean, where you have these oscillators which are coupled with each other.
Right. Yeah.
So there also one can ask the same question, right? There is Hamiltonian dynamics, and then you make a small change in the initial condition, and then look at how.
For this coupled map lattices, but you're asking for Hamiltonian systems. Hamiltonian is not. Yeah. I mean, that's not exactly what we are doing here, but that's something we are currently doing actually. Right, yeah. Like Fermi-Pascal, you can ask the same question for a Fermi-Pascal chain or a 5-4 chain, and right, yeah.
Do you see sort of similar things, or not clear yet?
We expect, but it's still like so for the Toda chain, that's something I worked out, and there you see exactly this. So this is like for quantum systems like free fermions or bosons. I mean, you see exactly this behavior, and even in classical total chain, you exactly see this. So that, so classical Toda chain, you can do the exact thing. Like you take or you just look at how you look at the linearized equations, and then see how a localized perturbation spreads. Right. So there, of course, you won't get the exponential growth because it's an integrable model. Right. But you will still get the decaying part. Right. So you will get the negative lambda behavior, and that has this kind of scaling form. Right, yeah, this 3 by 2. So this power 3 by 2 in many, for example, if you take a harmonic chain, you can compute this exactly, and you see this, you can see this exactly this. Or if you take free fermions in quantum case, also you get exactly this. Okay, so this is one interesting thing, that maybe there's a difference between integrable versus non-integrable version outside the light cone. So inside the light cone, of course, integrable models will be 0, and non-integral models will be finite, Lyapunov exponent. Right, yeah, these are all Hamiltonian. Yeah, yeah.
Lambda and so on. You try other things, you might see, for example, if you are applying a perturbation.
Yeah.
Suppose you, for example, add a perturbation to the Hamiltonian.
Add a perturbation to?
To the Hamiltonian.
To the Hamiltonian, right, yeah.
Right? So you will be going away from the integrable case.
Yeah, yeah. As soon as you go away from the integrable case, you should recover this.
Huh. So
right,
it might be interesting to study it systematically.
Right, yeah. Yeah, actually there are a lot of interesting questions, I mean, in this.
More questions? Very short comment. It's a really very interesting result. And concerning your maybe experimental evidence, I could suggest you the following. For example, in period doubling case, people in experiment, people prove that system going to chaos just when they able to confirm that there is a first and second period doubling. That's it. It's enough. So that means if you show the way to chaos, that means it's possible to confirm that it's going like you predict. The way chaos, not experimental confirmation of chaos, but way to this approach, yes. So you can think about it. Thank you very much again.